We've arrived at the point in the class where we're getting into one of the two basic ideas, and our basic idea that we're going to learn on this video is the idea of the derivative. So keep that word in mind and keep some of the processes in mind as well, because almost every question that I'll ask in the next several weeks will have an answer that goes like, well, you take the derivative. So let's consider the function f of x is x squared, a nice safe little function, and let's consider that we want to find the slope of that. Well, of course, you know the slope of this one is going to be a little more difficult. We're all aware of what the shape of x squared is, that parabolic shape. It's not a straight line, so the slope isn't going to be a nice number like it was on a line, of course. In fact, we're not even sure how to define the slope. So again, here's one more time, here's the picture. So I'm going to define the slope as the slope of the tangent line. In a tangent line, I've just drawn the green line on this graph. That's the tangent line. Notice it hits right there at 1, 1. So this would be the tangent line when x is equal to 1. Notice it's right on the graph at 1, 1, and then the graph sort of slopes away from it both before and after. It's the only point on this graph. 1, 1 is the only point on the graph that has both the tangent and the graph of the function in common. Otherwise, they move away from each other slightly. So if I want to find the slope of the tangent line, I'm going to call that, and this book calls that the slope of the graph, I'm going to have to figure out how to calculate that slope. And the way I'm going to start is I'm going to look at a couple of ordered pairs. I'll again base this function at 1, 1, and then I'll look up the road a little bit. I'll look at the ordered pair 2, 4. Now that's not on the tangent line, of course. It's close, but it's not exactly the tangent line. That'll give me 2 points where I can base a numerical calculation for the slope. So there are the two ordered pairs. X is 1, y is 1, x is 2, y is 4. One more time, here's the look at the actual tangent. So notice that the slope that I'm going to calculate here, using this what's known as a secant line, notice that it's going to be slightly taller, so it's going to be a little bit bigger number. So using change in y over change in x, I have 4 minus 1, that's the change in y, 2 minus 1, that's the change in x. And I found the slope of that secant line. Now this again is not the slope of the graph, but it's an approximation. That slope is 3. Again, I've drawn the tangent line, and if I were to maybe take a guess at what the slope is, I could look at the ordered pairs 3, 5, and 1, 1. I would probably venture that the slope of the tangent line is somewhere around 2. So let's see if we can maybe refine our estimate using a sequence of secant lines. We started with 1, 1, and then 2, 4 as my two ordered pairs. I'm going to move that second point in a little closer. Notice I've expanded the picture. I've sort of blown up the picture. I'm focusing at that 1, 1 pair. So the second ordered pair I'm going to use now for my second approximation of the slope is 1, 1, and then the ordered pair 1.5. And when you plug 1.5 in and square it, you get a 1 or a 2.25. So we have 1, 1, and then we have 1.5, 2.25. That's the second set of ordered pairs I'm going to use. And again, by making this interval smaller, we should get a closer value to the actual slope of the graph. It's similar to what we did with dropping the rock off of the tower, or also with the car travel that we looked at in the last activity. As we shortened the time period, we got a better estimate for the average speed. As we shortened the time period, we got an better estimate for the average speed, both for the car and for the rock. So we're going to shorten our distance here between the 2 points and get a better calculation for what the actual slope of the graph is. Taking the change in y over change in x one more time, again we get, in this case, a 2.25. So we move the points closer, we move the points closer, and the closer we get them, the better our estimate is. So here's a quick summary. Here's where our baseline point, 1, 1. We then compared 1, 1 with 2, 4, and then we compared 1, 1 with 1.5, 2.5. Connected those points. Now we're going to look at the ordered pairs 1, 1, the original point that's on the graph, and we're going to compare the slope there where we send the next ordered pair is 1 plus h, comma, 1 plus h squared. So plug in a 2, get a 4, plug in a 1.5, get a 2.25, plug in a 1 plus h, get a 1 plus h squared. So again, the top one and the bottom one, those will be the two ordered pairs that I use to calculate the slope for this third set of for the secant line. Plugging that in, the change in y over change in x, it'll work just like the other two have worked. We will take 1 plus h squared, and this one should be fairly familiar. We did a lot of work like this in the activity today. So we'll square out the 1 plus h, we'll get a 1 plus 2h plus h squared. Subtract 1 from that. In the denominator, take the difference between the inputs, 1 plus h and 1. Notice when we do the calculations, there's some simplification we can do. 1 minus 1 cancel to 0. And notice now that in this difference quotient we have an h in each of the points. One of those h's will cancel, and we're left with simply 2 plus h. That should be the average rate of change. And just as we did in today's activity, I want to make sure that this is accurate. So using the points that we had, notice that with the average rate of change, I've written that there as 2 plus h. And the first set of ordered pairs, where I went from 2, 4 to 1, 1, that h, that distance between 1 and 2 was 1. I found the average rate of change was 2 plus 1 was 3. Go back and look earlier. I found that the slope of that secant line was 3. The second set of ordered pairs was 1.5 comma 2.5. I compared that to 1, 1, and I found the slope of the secant line there was 2.25. That's consistent with my formula 2 plus h. H was 1 in the first case, I get 3. H was 0.5 in the second case, I get 2.5. So I'm fairly confident that I have the right formula here. Now the instantaneous rate of change, that'll give me the exact slope. So I'm going to move that h closer and closer to 0, and as I move h closer and closer to 0, I find the instantaneous rate of change will give me a nice round plug in h equals 0, end up with a 2. That'll give us the slope at x equal to 1. And I approximated that earlier, or at least I looked at my guess, and that was what I had for a guess. So now let's consider what the slope is at 2. At x equal 1, the slope was 2. Let's look at x equal to 2. I'm going to try this the same way I did before. I have my base point 2, 4, and then underneath that I'm going to look a little bit beyond 2 and calculate that out. So here's an example. Notice the bottom dot is at 2, 4. The top dot is a little further over. The x value is bigger. I'm going to call that 2 plus h. Now notice as I move the second dot closer to the first that I get the tangent line, or my secant line gets closer and closer to the tangent. So if I were going to do some calculations here to find the actual slope of the tangent line at 2, I would use this formula. Change in y over change in x. I would plug in 2 plus h. I would plug in 2, calculate those values on the top, and then the difference between those inputs on the bottom. I'd take 2 plus h squared minus 2 squared, 2 plus h squared minus 4, and then divide that by h. Squaring out 2 plus h should be old hat by now. 4 plus 4h plus h squared. Notice the 4's subtract off. Notice each term now has an h in it. We'll cancel those h's, and we end up then with 4 plus h over 1, or simply 4 plus h. There's the average rate of change. Now if I take that limit as h goes to 0, as I move those points closer and closer together, I can calculate that the slope at x equal to 2 is 4. So let me sort of recap what we've done so far on this video. I calculated the slope at 1 by looking at this, what's known as a difference quotient, and then eventually I let h go to 0, and I found that the slope was 2. Then to find the slope at 2, I looked at this difference quotient, plugged in h equals 0 after I calculated that difference quotient. I found that the slope was 4. If I want to find the slope at every point, I can do so. So instead of specifying the 1 or the 2, I'm now going to calculate the slope at every point, x. The same mechanisms are going to be in place. I'm just going to replace that known number, 1 or 2, with this unknown number, x, and watch how the mechanisms work. We'll take f of x plus h minus f of x over h, f of x plus h, remember the function says to square whatever the input is. The input in this case is x plus h. I'll square x plus h. I'll subtract x squared from it and then divide by h. Well, squaring out the x plus h again should be old hat, x squared plus 2xh plus h squared. Subtract off the x squareds. Notice those two like terms vanish. Notice each of those terms again has an h in it. Cancel those h's out. And now our last part on this one, to move this from an average rate of change to the instantaneous rate of change, is to take the limit as h goes to 0. What we're left with here is a nice formula. The formula for the slope of the line at any point is also known as the derivative of the function. And the derivative can be written either way. We'll most often use in this class, we use the f prime, but also notice there's an alternate. It's a dy dx. Both of those are just fine. The derivative of the function is 2x. That function tells us the slope of x squared, or original x squared. That function tells us the slope at any point. For example, here I've drawn the tangent line at x equal to -2. Remember, the formula for the slope is 2x, so 2 times -2, the slope here is -4. In fact, if you look at a couple of those points and you calculate the slope, you can convince yourself that it's -4. Here at the bottom of the graph, we have a slope of, where x is equal to 0, we have a slope of 0. In my third one here, I've made the tangent line go through at x equal to -3, at x equal to -3. Remember, the formula again is 2x, so the slope here is -6. We now have a formula for the slope at any point, and we can use that to calculate the slope at any point. So it's an instantaneous rate of change. And here's the formula we're going to use for every single derivative that we could take. It's the limit as h goes to 0 of f of x plus h minus f of x over h. Notice there's 4 things going on. There's the f of x plus h, there's the f of x after it, so we have to subtract those two, we have to divide by h, we have to take a limit. So I'm going to introduce you to a 4-step process for taking derivatives. Let's start with this function. It's a different one than before. It's again a quadratic, but these quadratics are a nice entryway into some of the harder work we'll do later. Step 1, let's find that f of x plus h. Well, f of 7 is 2 times 7 squared minus 3 times 7. F of 21 would be 2 times 21 squared minus 3 times 21 plus 4. F of x plus h, I'm going to use the same sort of logic. Any place an x appears in the original, I'm going to substitute in x plus h. So let's see if we can calculate and simplify 2 x plus h quantity squared. Notice I put x plus h where x was in the original, minus 3x plus h plus 4. So let's square out the x plus h first, and then don't forget to distribute the minus 3. Here's a really important part. If there are mistakes made in this part of the algebra, usually it's with the minus sign. So squaring out the x plus h, multiplying x plus h times itself, we get the 2 times x squared minus 2x, whoops, that should be a plus x squared plus 2xh plus h squared. Notice I've distributed the minus 3 through the set of second parentheses. And now distributing the 2 through, there's my final f of x plus h in simplified form. So all of that just to get step 1 done. Now in step 2, we subtract the original function from the function we just created. So we're going to subtract this 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 4. Subtract from that the original. And notice I put that second thing in parentheses. We have to be careful. We want to subtract every single term. So we'll have a 2x squared minus a 2x squared. They'll cancel. We'll have a negative 3x minus a negative 3x. They'll cancel. We'll have a 4 minus a 4. They will cancel. So we've calculated the difference between f of x plus h and f of x. There it is. Step 2 is complete. Now in step 3, here again is my definition for the derivative. Step 3, we will divide what we just got done doing by h. So there's our numerator, 4xh plus 2h squared minus 3h. Notice each of those has an h. We will cancel an h from each, and we'll be left with 4x plus 2h minus 3. Over 1 or not over 1, it doesn't really matter. Now we're finally to the 4th step. The 4th step is take the limit of that difference quotient. So if we take the limit as h goes to 0, that's one of the easier ones we'll ever do. Plug in h equals 0, and we find that the derivative is 4x minus 3. What will that derivative give us? Well, in the short run, it'll give us the slope at every point. So if I were to draw the graph of 4x minus 3, and I were to ask, what's the slope of the graph at x equals 5, for example, all I would have to do is plug 5 into this first derivative formula, and I could find that the slope is 17 at that point. Now, the question might arise, do we have to run through all this algebra every single time to find the derivative of a function? And the answer is no. I've designed the next activity to show you some of the amazing results we get. And in fact, we will look at any function of the form f of x is x to an n. And there's a nice formula that's going to work for every single one of those. So I look forward to introducing that to you the next time we have class.